Let's talk about project 4, lesson 17. So the figure shows the elliptical orbit of Mars, where each unit of the coordinate plane represents 1 million kilometers. As shown, the planet's maximum distance from the Sun is 249 million kilometers, and its minimum distance is 207. The Sun is at one focus of the ellipse, and the center of the ellipse is at the origin. What are the coordinates of the Sun? So we're trying to find the coordinates of the Sun. Now, one of them is given to us freely. As we can see, the Sun is sitting on the x-axis, which means the y-coordinate is 0. But before we dive too much deeper into that, let's just review the question, make sure we understand what's going on. So we're given this figure, which shows Mars. So here's Mars orbiting in this elliptical pattern, and we see the Sun. Now, we see that the planet's maximum distance from the Sun is 249, which is shown right here. So when the Sun is furthest away from Mars, the distance between the two is 249 million miles. When Mars swings back around on the other end of the ellipse, we see that it comes to a minimum distance of 207 million kilometers. Now we see the Sun is at one focus of the ellipse, and again the center here is the origin. So I want to know the coordinates of the Sun. Really, again, because the Sun sits on that axis, I know that the y-coordinate is 0. So I'm just trying to find the x-coordinate of the Sun. So to find that, I need to ask myself a few questions. So first, what is the distance from one vertex to the other? I can see that the segment from here to here is 207. I can see the segment that from the Sun to here is 249. So if I add them together, that tells me the total distance from one vertex to another. So that's important to consider. Now, if the center is at 0, 0, what is the distance from the center to the left vertex? Okay. Now, I'm asking these questions because I'm trying to figure out some measurements, and eventually my goal is to measure the distance from the Sun to the origin, because that's going to tell me the x-coordinate. So right now, I know the total distance from one end to the other. I know the distance from the Sun to the far end of the ellipse. I know the distance from here to here, right? I'm trying to find this other segment that I don't know yet, and that's why I'm asking these questions. So if the center is at the origin, what is the distance from the center to the left vertex? So from the center to the left vertex would just be half the total length that I just figured out here, right? So if I added this number together and took half of it, that would tell me the distance from the center to the left vertex. Now, if the distance from the Sun to the vertex, so from here to here, is 207, what is the distance from the Sun to the center? What is the distance from the Sun to the center? So again, if you just figured out, we know the total length, which you calculated here. If I take half of that length, I know the distance from the center to the left vertex. I know that a piece of that is 207, so I need to know the rest of it to know the distance from the Sun to the origin. That is going to be my x-coordinate, okay? The distance is going to represent the distance from 0 to wherever the Sun is going to be my x-coordinate. And keep track of your signs here, okay? So is x going to be positive or negative when it's on the left side of the y-axis? Question 2. The figure shows the elliptical orbit of Mercury, whose minimum distance to the Sun is 29 million miles, which we see here, and whose maximum distance to the Sun is 43 million miles. According to Kepler's law, the average distance of a planet to the Sun is equal to half the length of the orbit's major axis. The average distance of Mercury to the Sun is how many million miles? Okay. I'm asked to find the average distance of Mercury to the Sun, and I'm told that the average distance of a planet to the Sun is equal to half the length of the orbit's major axis. So if I can find the length of the orbit's major axis and then just take half of it, that will tell me the average distance of Mercury to the Sun. So my major axis is the x-axis. As you can see, it's much wider on the x-axis than on the y. So I know x is my major axis and y is my minor axis. Now I need to know the total distance from end to end of this ellipse. Well, they told me the distance from here to here is 29, and from here to here is 43. So if I add 29 and 43 together, that tells me the length of the orbit's major axis. Once I know that length, I take half of it, and that will tell me the average distance of Mercury to the Sun. Now, finally, you're asked to write an equation that models the orbit of Mercury if the minor axis has length 70. So we already know that this length is, 29 plus 43 is 72. So I know from here to here is 72 million miles. And I've just been told that from here, let's use a different color. I've just been told that from here to here is 70 million miles. Great. So I need to write an equation using that information that models the orbit of Mercury. So let's consider, if the minor length is 70, what is half of that length? And what do I call each end of the minor length? So just consider that. What do I call each end of the minor length? Also consider whether I'm looking at a vertical or a horizontal ellipse, because that determines what type of equation I'm going to look at. So if my equation for this ellipse is x squared over a squared plus y squared over b squared equals 1, well, my a and my b are all that I need to fill in. So my a is going to be the answer from that previous question, right, when we found the average distance between the planet and the Sun by taking half of the major axis. B is going to be the answer to this, which is half of the minor axis. So I'll substitute that information in, and that will tell me an equation that models the orbit of Mercury.